Hi students, I'm Dr. Maya Dune. I'm coming back from chapter 4, Periodic Trends of the Elements, and this is the part 2. We discuss how to write the electron configuration. And also to wrap up the part 1 of chapter 4, we also discuss some rules that you follow when you write the electron configuration. So some of the rules, we started with Pauli's exclusion principle. What is the meaning of the Pauli's exclusion principle? Pauli's exclusion principle states no two electrons in an atom have the same set of four quantum numbers. Why? Because of the spin quantum number. Let me show you there. Okay, here. So here, because of the electron spin, these two electrons, helium has two sets of quantum numbers. And then we'll talk about Aufbau principle. Aufbau principle says electrons are added from the lowest energy orbital and then it's moving to the higher energy orbitals. And then we talk about Hund's rule. Hund's rule come to the picture when it filled electrons to the degenerate orbitals. What is the meaning of degenerate orbitals? Degenerate orbitals are orbitals with similar energy. So when electron filled in the degenerate orbital, first it singly filled, then it pairing up. So that is the Hund's rule. So keeping all this in mind, we started writing electron configuration. So we said, okay, always you need to follow this rule, like you fall 1s2, 2s2, 2p6. And also we talk about quantum numbers. This is like the whole picture, the quantum numbers, like, you know, when you go away from the nucleus, so it goes to the atomic orbitals. You have first atomic orbital, which is 1, 2, 3. And then each atomic orbital has its own set of quantum numbers, like each like example, if you think about principal quantum number 1, n equals 1, relationship with L is 0 to n minus 1. So you have only one s orbital. So that's what I write here, 1s. You go to the second shell, which is n equals 2. When n equals 2, L equals 0, which is s, and 1, which is p orbital. You go to the n equals 3 level, you have s, p, and d. You go to n equals 4 level, s, p, d, and f. It goes on like that. So it's a good idea. You write this in the exam, and so then you know how it's always filling the electrons. And then we wrote some electron configurations. So if I showed you, let me see, I can have closely today. See, when you write the electron configuration, let's take calcium, which is 20. How do you write the electron configuration? I start, okay, 1s2, 2s2, 2p6. I know it's 10 is gone, 2 plus 2, 4. And then you write 3s2, 3p6, and 4s2. So this is the calcium. This is how you write the electron configuration of calcium. Think about potassium, which is 19. You write the same thing. And also I showed you there is a one other way of writing it. You take the closest previous noble gas configuration, and then which is for the calcium, the closest previous is argon. So you can write calcium. All these are argon. So you write argon 4s2. And also I told you something else. By looking at where the electron configuration ends, it shows which block is it in the periodic table. And also the biggest period. This is 4. Biggest period shows which period that element is in the periodic table. So we wrote that, and then I'm going to go here. So, so this is the potassium, argon 4s1. So, how do you write the electron configuration? By looking at the periodic table. I'm telling you. Okay, let's write the periodic table of let's say take something. Okay, I say okay. Let's do gallium. Okay, gallium. So gallium is 31. Okay, and this one below. Gallium. Electron is the atomic number is 31. Let's see how we write it. So gallium 31. By looking at the periodic table, you see the gallium is in the period. What's the period? Period 4. So, and also it's a P block. So the electron configuration choose ends with P. I'm looking at the closest previous noble gas, which is argon. Argon is 18. You can write 1s2, 2s2, the whole thing, or else you can write gallium. It has argon because it's closest previous. And then you go, okay, 4s2, 3d10, 4p1. 4s2, 3d10, 4p1. You may wonder why I took 4s because it's 4, fourth period. First period, second period, third, fourth period, 4s2, 3d. Why 3d comes after 4? Because that's how it fills. That means 4 is filled first, then go to 3D. If you look at this diagram here, in this thing, you will see the order. Always 4s is small, s orbital is a small orbital. So s orbital fill first and then go to the d orbital. So that's why it's 4s2, 3d10, 4p1 because it's 1 here. So that's how you write the electron configuration. And I want to show you something, another thing that we also discussed yesterday. Just want to go over it again. Chromium and copper. So chromium and copper, you see chromium atomic number 24. So you expect the chromium to write like this. So you look at the periodic table, chromium is the closest previous is argon. 4 is 2, 3d4. So now when I draw its orbitals, 4 is 2, it's up, down, and then d. I have this d shell. 1, 2, 3, 4, 5. 1, 2, 3, 4. You see the d orbital has only 4 and d orbital is not even half filled. D orbital is very big. These bigger orbitals like to be at least half filled. In order to do that, what they do is S orbital is small. It doesn't matter whether it's filled or not a whole lot. It's better, it's filled, but the filling the D orbital is more important than filling the S orbital. So then the element take 1 here and then it shows in reality we see that the chromium, this is the correct one. 1, 2, 3, 4, 5. So now this is at least half filled. So that's why when I ask you the chromium electron configuration, it should be this one, you will see, not this one, because at least this is half filled. Similar situation with copper. Similar situation with copper. It is, when you write the electron configuration, it's 3d9. So it's not fully filled. So you need one more electron to be fully filled. So we take 1 and it's 4 is 1, 3d10. So that's how it filled the electrons in the elements. So here I have written the arsenic. Arsenic is 2, 2, 6 because always s orbital, the maximum number of electrons that it can hold is 2. P is 6 and the D is 10. So that's about the part 1, and then I'm going to the periodic table. We are talking some trends of the periodic table. And then we call these other main group elements. This is S block, P block, D block, and F block. We call lanthanides and actinides. And this shows the periods. And then Only noble gases have the fully filled p subshells, and then these are the d block. So, and then there's another thing. I told you, right, the groups or families, they have similar properties. Always, the family has some trends. So if you look at the periodic table, the electron configuration is always end with S1. Also, we call this number of valence electrons in the main group families are same. Example, group 1 has only one valence electrons. Valence electrons, the electrons in the outermost shell. Okay. So you need to know what are the valence electrons, what are the co-electrons. Valence electrons, electrons in the outermost shell is called valence electrons. Everything else, co-electrons. So let's do an example. Without using periodic table, give the ground state electron configuration and the block designation spt with an atom of 17 electrons, 37 electrons, 22. Classify each atom as a main group element or a transition metal. So 17 electrons, you start writing your electron configuration because you just fill 17. 1s2, 2s2, 2p6, 3s2, 3p5. It ends with p. It's a p block element. It's a main group. You take the other one, 37. You write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then ends with s. So it's a s block main group. Last one, you write and ends with D. It's a D block element. It's a transition element. That's how you classify. Now, now we are going to the other section, which is the effective So now we are talking about the properties in the periodic table, the characteristics, the trends. So before that, I want you to know what is this effective nuclear charge. So the effective nuclear charge is the actual magnitude of positive charge that is experienced by an electron. So what is that? So in think about the electrons in the shell. Let's go see the. Let me draw a diagram for lithium maybe. So I have here the lithium. Lithium has 1s2, 2s1, right? It's 3 electrons. So 1s2 is here, the 2 electrons here. And then the other electron is this shell. The lowest electron or the valence electron, how many protons? It's 3 protons. These closest electrons, they may experience the charge of 3 positive, but this electron will not experience plus 3. That much of an attraction will not experience the valence electrons. So even though you have 3 protons, it does not affect, so it has the attraction of 3 protons, it basically has 1.28. Effective nuclear charge, even though you have 3 protons, because of this inner electrons or co-electron shield, the effect of nucleus to the outer electron, we call that as the actual nuclear charge that the valence electron experience is effective nuclear charge. So if you see, this is the period 2, lithium, beryllium, boron. When you go from left to right, left to right in the periodic table, you see the effective nuclear charge increases. Why is that? If you think about beryllium, beryllium has 4 electrons instead of this one. Beryllium, let me draw again. So I'm drawing beryllium, which is 4 protons, then 1 and a 2. So now beryllium, because it has 4 protons, its shielding is still same because it's shielded by only 2 electrons. But you have more proton. Because of that, the beryllium electron experience better attraction. Same with boron. Boron has 5 electrons, 5 protons, So now beryllium experience more than that. So that's when you go away from the nucleus, because more and more protons adding to the nucleus, so effective nuclear charge increases. What is this effective nuclear charge? How stronger the outer shell electron attracted towards the nucleus? So you go to the next one, effective nuclear charge. How do you calculate it? In general, effective nuclear charge is given by effective Z, number of protons, shielding constant. So I'm not going to ask you to calculate it without giving the shielding constant. If I give you, it's just easy subtraction. But you need to know how it changes across the period. Like I want you to get more like a more theoretical, not the mathematical side, how it changes across the period, then what is going to happen to it. So because it's increasing the effective nuclear charge, the size of the elements across the period decreases. That's the thing you need to know mainly. So now when we study the atomic radius, there are different types of radius. We call atomic radius is just, and then the metallic radius like that. But think about the pattern in the no, sorry. So atomic radius, that's the one I want you to know. When you go across the period, atomic radius decreases. Reason? Because effective nuclear charge increases. So more nucleus attract the outer shell more towards itself, so it's slowly getting slower. So we call why the atomic radius decreases, because the effective increases. So that's the reason. So in the exam, if I give you, okay, magnesium, aluminum, silicon, phosphorus, arrange this in increasing radius, decreasing radius. Which one has the biggest radius? Magnesium has the biggest radius. Smaller radius, potassium, like that. And another trend, when you go down the group, the size increases regardless of the Z, because you add a whole new principal shell. So I like to summarize here. So we've talked about the first trend, which is the atomic radius. So what is the trend in the atomic radius? When it go across the period, across means from left to right, atomic radius decreases. When you go down, again atomic radius decreases. So this is how they show how it becomes smaller. See, it's big and getting smaller because see the effective nuclear charge increase as a reason. Question. Referring to only to periodic table, arrange element phosphorus, sulfur, oxygen in order increasing atomic elements. So increase, right? So the elements in the left side of the periodic table is biggest. So here, and then the smallest, when you go towards the right side, it's the smaller elements. So if you from left to right, you have smallest atomic radius is oxygen, because oxygen is the smallest and also it's on the top row, and then sulfur, because sulfur is in the third period, and then phosphorus. So this is how we think about it. Okay, because if you think about the periodic table, let me go show the periodic table really quick here. So this is what we're talking: oxygen, sulfur, phosphorus. Of course, we know sulfur and phosphorus bigger because it's a third period, but oxygen is smaller. Then it goes to the sulfur, and when you compare sulfur and phosphorus, phosphorus has much bigger radius because sulfur has more protons than phosphorus. So oxygen, sulfur, and then phosphorus has the biggest radius. And then I'm going to the ionization energy. Ionization energy is the minimum energy required to remove an electron from atom in its gaseous state. So basically, how easy an element can ionize. So you know metals, easily ionize. Metals easily lose electrons, resulting in iron, metal, they readily like to lose that electron. So this is the ionization energies. If you see, you just need to know the trend. You don't have to memorize any of these numbers. Just keep in mind metals like to lose electrons, so metals has very low ionization energy. And also, if you see the trend from left to right, these lithium and beryllium, they have relatively low. But if you go here, the neon, they don't want to lose electron. Non-metals, they don't want to lose electrons. So ionization energy basically increases across the periodic table. So the lowest ionization energy, easy to lose the electron. Similar, when you go down, it's easy to lose electron because the valence electrons are far away from the nucleus. When the valence electrons far away from the nucleus, the attraction to the nucleus is low, so that's why. And if you see this trend in ionization energy, this is the one period. Okay, I'm explaining one period. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So why it's if you're expecting it to be increased, right? Why it's like just like this? That is, you can explain this like little ups and downs from the orbital diagram. I mean, from electron configuration. So let's look at the this end. So it's this is group 2A. So here, let's take little beryllium. Beryllium, and then let me draw it, okay? Let me draw it for you. So it's easy for you to understand here. Okay. So beryllium, I have 4 electrons, okay? If I draw the orbital, so you have 1s2, 1s2, 2s2. So now I draw the orbital 1, 2, 1, 2. Do you think beryllium want to lose electron? Because it's fully filled. So that's why it has a little bit higher. Think about boron. 5 electrons. 1 is 2, 2 is 2, 2p1. 2 is 2, up and down, p, 1, 2, 3, or 1. If this p loses this p electron, it can easily come to the fully filled shell. Again, this comes to the idea that fully filled shells are more stable. So that's why beryllium has higher ionization energy, because it doesn't want to lose that fully filled configuration and go into the half filled configuration. But boron, in the sense, if boron loses that electron, it can easily go to the like 1s2 and 2s2 filled shell. Similarly, here, lithium, beryllium, boron, nitrogen and oxygen. Nitrogen, which is 7 electrons. I write 1s2, 2s2, 2s2, 2p3, right? Little bit higher. You see, 1s2, 2s2, 2p3, up, up, up. Okay, 2p3, it's at least half filled. But think about oxygen, which is 8. 1s2, 2s2, 2p4, right? 1s2, 2s2, 2p4, 1, 2, up, up, because of the, and then you have 1 electron here. If you lose this electron, it get at least half filled. So that's why it has a little bit lower configuration, a little lower ionization energy. That's how you can explain that glitch. Okay. Okay. So I hope I didn't make a mistake. Okay. Yeah, that's it. So that's how you can explain. And mostly you see in the D block, it's very difficult to talk about the periodic trends. We talk about periodic trends only in main group elements. And so that's about the periodic table. And I have this question. Would you expect sodium or magnesium to have the higher first ionization energy? So sodium and magnesium, so you look at the sodium and magnesium in the periodic table. So the sodium is here and magnesium. I would say sodium has, don't look at the numbers, I just want to compare. I would think the magnesium has the highest ionization energy because magnesium has the S shell filled. So sodium has low ionization energy, so sodium can easily lose the electron. But think about the second ionization energy. Second ionization is when the sodium loses its electron, it has the neon electron. It gained the neon electron configuration. It has very high ionization energy because when sodium loses that one is electron, it goes to the neon configuration, which is fully filled p shell. The second ionization energy of sodium is extremely high. Sodium loses its electron very easily, but sodium never forms. So when sodium loses its electron, it forms plus one charge, plus one ion, but sodium never forms plus two. But magnesium doesn't want to stop by losing one electron. It always go to the second ionization energy because always magnesium form plus two. Okay, I think I'm going to stop the ionization work from here and I hope this video is helpful.